I bought yesterday.
What is?
Chocolate mousse cake.
Okay.
I don't know.
Didn't want a nice bowl of porridge, no? I already had porridge for breakfast, but so wet outside I thought the second bowl was nice.
Not that late.
No, but I don't know where Jerry, Sean... Yes.
I'm the first.
You should have been the first, you live here. And in fact, where's Lee? He's down on the ground floor. Oh. Do you have Excel open? Yes. Okay. Chrissy, you got your laptop?
Yeah.
So for this tutorial, as an example of what to do, we'll imagine we have some voltage and current. So here we put the voltage and here we put the current. Come on.
Oh, we need computer today?
Yes, do you have it?
No.
Oh, go get it. Come on, quick.
Yeah. I thought you said we do this in assessment support, the Excel.
I don't think I said that, did I?
Yesterday, I'll pass some stuff.
Oh, really?
Use that time.
Okay.
And anyways, if I said that, why did everybody bring their laptop?
Okay,
You know, use the evidence, man. Look at the evidence. Right, so if you can type the same numbers as me, it'll be easiest. 0, 1.1. Come on, Jerry.
No,
Teacher,
Yes,
I saw two Japanese on the street.
you saw 2 Japanese on the street. What are you saying, man?
What?
Is this
it's really a first to
Is this a
speak
big
Japanese.
deal?
Yeah, they speak Japanese. I saw English. And I said Ohio. I thought so stupid.
It's not like Japanese people are some small, rare group of people. There's like 120 million Japanese people.
I mean, in the school, you only have one Japanese.
Is it?
Yeah, in the school.
Yeah.
Yeah. But I'm
It's
sure
really good.
there's a lot of Japanese people in Dublin, no?
Yeah, just like a few, like 10.
Ah, no, it has to be more than 10. Right. Anyway, she says hello to them.
No,
Nice.
in Japanese.
What did you say?
Ohio.
Konnichiwa?
Ohio.
Ohio? Is what?
Good morning.
Oh, good morning, okay.
Is that?
Konnichiwa.
Konnichiwa, I thought was hello.
Ohio, konnichiwa, yes.
Yeah.
There you go, okay. I know some other Japanese as well, but I won't say it.
Teacher, what kind of word I don't know. My language.
Yeah, what's it?
Yes, this one I know actually.
I can't speak Japanese.
Don't do this. One of my Japanese students told me this a few years ago.
What?
So I know that Ohio and Konnichiwa. So a very limited vocabulary. All right, did you type these in?
This is so good.
I bet it is. It's chocolate rice. Did you type these voltages in?
Yeah.
You have them, Monica? Chrissy, do you have these numbers typed in?
I'm doing that.
And what exactly are you going to do though? Do you have Excel on your phone? Oh.
Download Excel on your phone.
I do.
It's too hard. I can't do it myself.
Where's your laptop?
I didn't remember that.
Ah, Jerry.
I don't know. We have.
Okay, well, can you take it?
Yeah, we need a laptop or camera.
This well, you after all this.
Yes, but can you take out some pen and paper at least so you can write down the functions?
I mean, I can see it.
But I would feel better if you had pen and paper, please.
I don't know.
Or it's on your camera.
Okay, so let's go 0, 2.3, 4, 6.2, 8.1, 10, 11.9, 14.5, 15, 16. Okay, if you can type these numbers in exactly. Do you know what? I think I'll just change this V to PD. I think it's more usual nowadays. Potential difference. You got those typed in? Good job. How can he be faster with a phone than you with your laptop? Goodness sake.
What are you doing, man?
He's distracted by the death of Stephen Hawking. It's weighing on his mind.
Oh, really?
He just told me in the news this morning.
Peter, do you need a laptop for math?
What happened to this, man?
No.
We have math
Yeah.
For physics you needed it.
and chemistry.
What? No, haven't you?
No, we need that.
For what?
We have assessment for today.
Yeah,
Cherry.
I don't want to do that. It's too heavy.
Continue, can I continue? Why is taking this guy so long? Is he KJ, is he ready there? He has them all?
Yeah.
Alright. So, to begin, let's explain the basic idea here for what we're doing. So, in this Excel lesson, we want to do three main, we have three objectives. The aim of this lesson is to calculate the resistance, but we're going to do this by three objectives. Firstly, we're going to make a plot of the data, but this is real life. The data should be a straight line, but it might look something like this, roughly a straight line. So then what we'll want to do, we want to get this line here, which is called the line of best fit. Now, I think it's good if you write these terms down, because these are terms you can use in your report. And the method for finding this is called least squares. And this is the method that is used by Excel. So if you can make note of these terms, please.
What's this?
Yeah, please, Jerry, if you got pen and paper.
Excel.
Oh, fine. But what about writing this down? Okay, fine. Continue?
Yeah. Oh, wait.
Continue? Lee? Yeah. So this is what Excel does. It tries to fit a line, and then it looks at all these little distances here. Can you see them in yellow? These small distances here. If the line is really bad, like this line is really bad, then if you look at all these distances between the line and the points, it'll be really big. What Excel tries to do is it searches for a line that will make all these distances as small as possible. Okay? These distances, these are called Y residuals. In other words, it's kind of like the Y errors. It's the difference between the data and the line for the Y, for the height. That's what Excel tries to minimize when it finds the line. In a perfect world, you would want this to be 0. What would that mean? It would mean all the points are on the line. But of course, that can never really happen. this is more vocabulary you need. These are called Y residuals. Did you write that down? Y residuals?
Teacher, do you get that? Putin.
Hawking.
Hawking.
Yes, no, not his Chinese name, his English name, Hawking. Yes, yes, I heard, yes.
He's already 73 years old.
Something like this, yeah.
I think she's 40.
I thought he's only 40. Wow. Okay, no, he's much older than 40. Okay. Now, let's go on, and then we would want to find this line, y equals a plus bx. Okay. So, first thing, let's make the scatter plot. So if I go back to my Excel, in this program, the way I would do it is, first I would highlight this, and then pick Insert Chart. Okay. The chart type you want to pick is called scatter. Like this. Yep. And then we'll go next. 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 Okay, now on this screen, we do not want a legend. So, one tick. And we do want to show the X and the Y lines. So tick. If you don't have these options, I think in Excel they give you the options after the graph. You can click it and then change it. The title, so what title will we give this? This is potential difference against, no, it's not. It's a current against potential difference. And the subtitle is the IV curve, because that's what we're looking at here. The x-axis is potential difference slash volts, in volts, and the y-axis is current in amps. Okay, let us have a look now at our graph.
How to do that?
Do what? Do what?
Like entering title, subtitle.
Now this is a little bit too big, so I'm just going to shrink it down for my screen. So you all should have something that looks kind of like this. Do you all have this drawn? Not yet? Okay. Yeah. What's the problem?
Insert.
Chart. Scatter. Yeah. What the fudge? But I think you can change it here in format.
Okay.
Oh, no, hang on. What the heck? Dude. It's because it's an apple. That's the sign. Yeah, I think you can do things like add elements, so then this is where you can add in like axis title, so you can put a X title here. So I think you have to do it bit by bit.
Okay.
Yeah.
Okay.
Apples. Huh? Really? So it seems like the LibreOffice is a bit easier here. What are you talking about? Look how much quicker I'm waiting here for you to catch up to do this.
This one.
No, this is what it is wrong. Go to the type.
Nope.
No, with the
No curvy wiggly line.
Here, click here. No, next one. Next one. This one first. And then add a track line here.
Still have to tell 1 by 1.
No, don't. Just scatter plot. No trend lines, no curves, no lines at the moment.
Oh, nice one.
Yeah. Who? Am I waiting for you? Okay. Am I waiting for you?
No.
Are you sure?
Do we have to check the our range to 0 to 20?
Oh, no. Once it looks like this, roughly.
Okay.
Yeah?
Yeah.
Continue? Lee? Chrissy? Monica? Yeah, okay, so the next thing I want to do is on the graph add in the trend line. So for me, if I click one of the points, come on dudes. Come on. No. Line, is it? Son of a... Oh, come on. Oh, there we go, I got it. If I highlight my point, I can right click and pick insert trend line. Or maybe you have a button up the top to pick insert trend line. Like, you probably have add element. It's the same, like this. Insert trend line. Now when you're inserting the trend line, make sure you have linear, and also you can have these two things ticked as well. Show equation, show coefficient of determination. These two you need as well.
What?
You mean R squared?
Yeah.
Oh, okay.
Can I hit OK?
Right.
KJ? Can I?
Here.
Chrissy? Can I hit OK? Yeah, but I mean, do you see everything you need to on this? I need these two, R squared and show equation, and linear. Yeah? So, let me just move this.
Just when I put this here.
There you go.
Oh yeah, I see.
Okay. Have you all added this to your graph? So the first thing is pretty obvious. What is this first line telling me? The equation of the line. Okay, that's pretty obvious. But does anybody know what the second thing tells me? This 0.99.
Resistance.
No?
How
The distance
that
between each point with the
Kind-
if it close to 1 is more away from
Yeah,
here?
yeah. If this value was 1, it would mean the points perfectly fit the line. And if this value was 0, it would mean completely not fitting the line. So a value of 0.99 is extremely high, so it means the points are reasonably, or more than reasonably, lined up. So in your report, you can comment on what's called the coefficient of determination. And you should comment on how close or not you are to 1. Now really, I hope that everybody should be in the 0.9 or higher for this. Okay. Now, for me to continue and to make space, I need to delete this graph. You can just move your graph off to the side, but I'll need to delete it. So is there any questions before I delete this graph? Can I delete it? Yeah?
For the y-axis unit.
Yeah.
It's fine.
Huh? No. This is just how my program displayed it.
Okay.
Can I delete it now? You can just move it out of the way, okay? I'm going to delete it. Okay, so what we need to learn now is how can we calculate the A and the B in Excel. So this is called the, as you know, the intercept, and this is called the slope. I want my red. There we go. Okay, let's have a look. So, first things, let's see, I'll just put the results maybe here. So the first thing I would like to calculate is the intercept A, and then the gradient B. Because now we're going to look at y equals A plus bx. Right, so Excel has the function built into it, which is quite nice. So here we just type in equals slope, intercept, I-N-T-E-R-C-E-P-T, bracket. And you see how it's telling me to input it. It says first put in the y, then put in the x. So first I'll highlight the y's, comma, then I'll highlight the x's. So this is, for me, this is what I have to have here. Yeah?
Do we have to capitalize?
I don't think you have to, but it's usual in Excel to use capitals for your function name.
Why is not A to 11?
I did. Oh, I guess I just missed it when I was highlighting it. Yeah, thank you. Okay. So what value did you get for the intercept?
Minus 0.
Minus? No, it should be a positive. Oh, intercept, sorry. I was thinking the gradient.
Minus 0.282.
Yeah. Can I continue?
Yeah. No.
Sorry, what?
There.
No, ready.
Oh, well, I'm going to enter it now.
Negative 3?
Yeah, minus.
From B2 to B10.
B11?
Whatever.
Yeah, and then A2 to A11.
Maybe someone.
How different is it?
0.512.
Oh yeah, you do 3, man.
Look, it doesn't really matter because this is made up data. We're just using it as practice, so don't worry about it. Okay, can I go on to the next part? So, the name of the function here is slope. And again, bracket, highlight the y's, comma, highlight the x's. Yep.
Yes, it's related to P.
I'm thinking.
How do I shrink this
Can you
down?
click the 2 point something there?
Got it, man? Can I continue? Monica, Lee, Christy? Yes, I can continue? Okay. So the next thing we need in our calculation is what's called the predicted y's. So what I mean by that is, imagine you're here, and imagine we have a data point. Let me just put it here to make it clearer. So this is our data point. So this has an x value, which I'll just write here as x, and this has a y value, which I just write here as y. But if I was to put x into my line, it doesn't say that the y is this. Instead, it will say that the y is this. And the symbol we use for the predicted y is y with a little hat on the top. Now, can you see that this distance here, this is like the residual, this is the error, this is the difference between what the line thinks the y should be and what the real value of the y is. We will need to calculate these residuals, which I represent with this letter. But before I can calculate that, first I have to calculate that. And the way I calculate this is I take my x and I put it into the formula. If I put this value of x into the formula, then the answer I get will be this. So, going back to Excel now, I'll call this y hat. So, this is equal to a. Now, please be careful. A is a constant. It doesn't change. So we need to put our double dollar signs on it. Dollar, dollar. Plus b. Does the b change? No. So again, dollar, dollar. And what does this multiply by? The x. And what's the x here for the first one? What box is that in for the first one? What's the first x value? It's this one here, A2. Yeah? So if I click that, I get this. Now that's actually really really useful to see, because we can see that the real value was 0 and the predicted value is minus 0.28, although we kind of knew that because that's the intercept. If I grab this and pull it down, yeah, I have all the predicted heights. These should all be similar to these, and they are. You see, this is 16, this is 16.04. This is 15, this is 14.36. Okay, so I need you to make this values here. Okay, have you done that? Yeah? Oh, once I type the first formula in, you just grab the corner and put it down.
Why do I have a value when I continue to go down?
Huh?
I have a value when I continue to go down, but I have no data at that point.
What do you mean?
I mean, I can still go down by 1.
Ah, it's probably taken these to be 0.
Oh,
Are they all the same?
yeah, I think so. Yep.
Are they all minus 0.28?
Mm-hmm.
Yep. Because you're just getting, you repeating for x is 0. Okay, continue? Yeah. Now the next thing we need to calculate is what's called the y residual. And as we said earlier, that's the difference between the y value and the predicted y value. So actually this formula is kind of straightforward. What would I type in here to get the residual? Equals what? I want the difference between what was predicted by the line and what was observed by the experiment.
Y hit
A4 minus.
Yeah, it will be B2, because that's the y value,
Oh.
minus y hat, which in this case would be E2. Now, before you type that in, we only care about the positive difference, not the negative. So in other words, we don't want these to be negative, we only want them to be positive. And the way we do that in Excel is we type in ABS, that means absolute value, bracket, okay, and then it's B2 minus E2. So you should, all of these should be small numbers when you drag them down. Okay, can I drag these down? Yep. And you see they're all small numbers. The smaller the better. Okay. So what we also need to know in Excel for later is what is the average residual, y residual. So at the very bottom here we'll just stick in equals average bracket, and then we'll highlight all of these. Got that? Yeah. Did you get 0.34? This is the uncertainty in the y residual. Okay, can I continue now? So now we have to repeat this, except this time we need to repeat it, but we need to look at the x residuals. So for example, that would be looking at the difference between this point and what we think the x value should be. So this one here was the y residual. This one here would be the x residual. Now there is kind of an easy, sneaky way to do this. The easy, sneaky way to do this is you think about the problem like this. You say, okay, well now this time what I'm going to do is make the graph, put y here, which is the current, and then here I'll put the potential difference, which is the x, and then I have my line, and then this line will say it's x equals a dash plus b dash y. So that means if I have a data point here, if I want the x residual, I just look at this. So in fact, if I just repeat everything but swap the x and the y, I can get the x residual quite easily. So it just means here I have to recalculate these. So this time I'll call them intercept a dash, intercept b dash, and my formula is now going to be x equals a dash plus b dash y. Now I'm going to copy these two formulas down. Hopefully they should stay the same. No, they don't, so okay, I'll retype them then. Okay, so equals intercept, but please be careful, you're putting the x and the y in backwards, so first I'll copy the x, then I'll copy the y. And then for the slope, first I copy the x, then I copy the y. And now I have these. Yeah, same numbers. Got that? Yeah?
No.
Here? Okay, continue. So now we need the x hat. So by using this formula, we get equals a, the new a, with the dollar signs, dollar, dollar, plus the slope with the dollar signs, dollar, dollar, times the y value. So for this one it would be b2. And I get that.
B2.
Yeah. Continue. I'll drag these down. Yeah.
Can you click the y residual value?
Okay.
Y is IA.
Huh?
Y.
What's your question?
X plus BY.
X be y.
Y.
This one?
Yeah.
What are you asking me?
Yes.
Are you asking me anything? Okay. Can I continue? What's the next thing here? I need x residual, which will be absolute the difference between the x value, which is a2, minus the predicted x value, which is g2. So again, a small number, and I'll drag these down. Yep. Now, underneath here, I'll put in the uncertainty in the x residuals, and that will be equal to the average of all these x values, x residuals. So I get that number there. Yeah? Can I continue? So the next thing I need is what's called the ratio here. And what I mean by ratio is, I mean the ratio of the y to the x. So that would be equal to this number here, look, this one, the y residual uncertainty, divided by the x. So I should get about 2 here. Yeah.
Y divided by x.
This y divided by this x, yeah. Next, I need the square root part in my formula. And if you remember, this is the square root, SQ or T, of how many points I have. How many points do I have in this experiment? How many data points? 10, isn't it? So square root 10. So now on to the juicy part, which is the uncertainty in the slope, which is we call B in this lesson. So if you were to look at the worksheet from yesterday, the formula was this number, this ratio, divided by the square root of the sample size, and I get 0.64. So what I'm saying here is that the slope can change by as much as 0.64. That's the uncertainty in it.
What is the formula for the ratio?
Y over x.
Yeah, I did that, but I have different answer. Oh,
0 x equals
this is only copy.
Continue?
Actually, so it's different.
Guys, can I continue? Yeah.
What's
Yeah,
the formula
now
for
that's
SQ?
What's the form for SQRT? Funny enough, it's SQRT.
Oh, okay.
Isn't that funny? The formula for SQRT is SQRT. Who would have thought it? Alright, continue? Yep. So now we're into our result. When we think about the IV curve here, remember we said the resistance is equal to 1 over B in this case, the slope. Yeah? So if I just put down now over here, or equals, well, we know what the or is. It's going to be 1 over, which number on my screen here? Which number would it be? For the or, it's 1 over,
B.
yeah, but which box is that?
D.
Yeah, D3. And I get this. Now, what's my uncertainty in the or? What's that? What number is that? You see, it's not this. Why is it not this? Anybody know? Well, because this is the uncertainty in the slope. And it's not the slope we care about, it's 1 over the slope. In other words, if I say or equals 1 over B, and I know the uncertainty in the B, then I could know the uncertainty in the or by using the rules from yesterday. We have the rule that the uncertainty in the or, you see, if I change this into B minus 1, I could say the uncertainty in the or is the average or value, or in other words, the predicted or the or we think, square root minus 1 squared, and on the top here is the uncertainty in the b over the value of our b. And now I can actually simplify this. This actually simplifies down to r times the absolute value of the uncertainty in b over the b value here. Because the square and the square root cancel, and the reason I have absolute is because square root's always positive. Shouldn't get a negative answer here. So it's, now if I look at my data, this is actually can simplify even more. Is this positive or negative in my data? Positive. And this here? I got a positive number, didn't I? And my value for b, the slope? Positive. Yeah. So I can just change this into my resistance times my uncertainty in b divided by my value of b. So let's put that in. So equals resistance times F17 divided by b, wasn't it? So that's D3. Yeah. So I get 0.148. So if I scroll down now, I think my result is or lower or upper. In other words, the smallest value I think or could be and the biggest value I think or could be. The smallest value I think or could be is going to equal this minus, yeah, so it's equal to that, no, it's equal to that minus that, and the bigger value could be that one plus that one. There's a bit too many decimal places here, so what I might do is just round this off, so that equals round bracket this one. We'll do 2 decimal places, I think would be suitable. And this one here is round bracket this one comma 2 decimal places. So by doing this experiment and this analysis, I have a very good answer here. I can say the value of the resistance of the resistor is between 0.33 and 0.63 ohms. Or in other words, I could just simply say or equals 0.48 ohms plus or minus 0.15 ohms. This is basically my result. This is the result. For which? Oh yeah, just add and subtract.
So get around the R and do R to decimal point 2.
I just did my one. 2 significant figures seems reasonable for your results.
Is it the same formula when you round off in Python?
Yes, I think so. Continue.
So the upper one is plus, right? R.
Yeah, of course, yeah. Now, I should say, when you go on to university, you'll do very similar calculations, but there are many things I simplified in this process for you. The formulas I simplified, they're a little bit more complicated. For example, really I should have divided by square root n minus 2, but why is it n minus 2 and not n? Or why is it even square root? And my formulas I used here, there's actually more complicated formulas, but the formulas I used up here to calculate these residuals, although they're much simpler, they're actually still very close to the values you would get if you used a more advanced method. In other words, I took an advanced method and really simplified as much as possible without changing the answers so much. Okay. I need to delete all of this. So can I go to a new tab? Because we need to talk about what you need to do for Newton's data. Can I go to a new tab? Yeah. So if you just think about this, the difference with the Newton experiment is you're making a graph like this, where on this axis is the force and this axis is the acceleration. And what would the slope here represent? Who's there? Is it Sean? Come in, Sean. What happened to you? What happened to you? A lot. Leave me alone. What does the slope represent here? Now think about it. Is it mass? If I say F equals ma, then A equals 1 over mf. Yeah, so the slope is 1 over the mass. So the mass is 1 over the slope. Okay? If you use this formula to make this graph, and if you use this graph to get the mass, then what you're doing is you're predicting the mass of the system using Newton's second law. So you predict mass from F equals ma. You're shaking my table. So, why do you care to do that? Because you know what the mass is. You measured it, didn't you? So if the mass that you predict matches the mass that you observe, then you have evidence for Newton's second law. This is how it works in physics. If you have a formula, you use the formula to predict something. Then you measure. If your measurement matches your prediction, then you have evidence in favor of the formula. So that's why you had to measure the mass, and that's why you had to keep the mass constant. Because you're going to predict the mass, and hopefully your masses should be the same. Now, of course, they won't be exactly the same. Why not?
Human error.
Yeah, human error. So what you need to do, not only do you need to predict the mass, but you need to put some kind of bounds on it. So maybe your prediction for the mass will be, say, I don't know, like 1100 grams to 1180 grams or whatever. So that means for this to work, you need the true mass to be between these. If the true mass is between them, then you have evidence for Newton's second law being right. You understand? Now you realize this is very similar to the example I did, because in the last example I also needed 1 over the slope. But what's a little bit different for Newton is before you can even get to this stage, you have to work out the F and the A. So let's think about how we can do that. If we have the trolley here and the weights here, what is the F for this? What is it? Yeah, the weight. And what's the formula of the weight? mg. But which m? The hanging m times g. Great, so we can know the F. But how can we know the A? Well, think about what you have. Because you have the two light gates, you can know a U and a V and an S. So you have V squared equals U squared plus 2AS. So A equals V squared minus U squared over 2s. So on your Excel, you should have a U, you should have a V, you should have the the S, which should be the same, and then you have the A. Then you have the hanging M, and then you have the weight, which is the force. And which two do you use? You use this one, and you use this one. And remember, this one here, this one goes on X, and this one here goes on Y. Now, please be careful, because somebody last year made a mess of something here. Listen. I don't want anyone screwing this bit up. You did each run twice. No, Jeremy, look at me. Look at me. Look at me. Look at me. You did each run twice, didn't you? The same mass twice. You do not take the average of the two. It's not the same as the pendulum. So you don't go U and then plus the other U divided by 2. Don't do that. You actually have both values here. Now they should be pretty close. So like you might have something like 0.1 and 0.11, and here could be 0.5 and this could be 0.51. And then the next one might be 0.2 and 0.2. You know, maybe for the next one they were the same, because I think that happened for someone. Okay, you do keep them all. You don't take averages of 2s. Okay, you do keep them. Now, that means when you make the graph, it would look a little bit like this. That your points should be looking like they're in pairs. Because every two values are close together. And that's fine, okay? So you do include all the UV measurements. You get all the A's and all the F's, and then you repeat everything we did here. And at the end of it, what you'll have is a mass plus or minus an uncertainty in the mass. And you want your measured mass to be within this predicted range. So you want something like, for example, 1150, and that is in 1160 grams, plus or minus, let's say 100 grams or whatever. That's what you want. That verifies Newton's second law. Do you understand, Jerry? You sure? Everybody understands? Yeah? Yeah.
It's not included.
Then you screwed up. You screwed up, and some people, what they would do in such a situation is they might slightly change their data to make it work. Now, of course, I would never suggest that you do such a thing. It would be quite bad. But some people, if they know what they're doing, can carefully adjust it. Just saying. Okay. So what I want you to do for the remainder of this class is I want you to get a start on inputting your data into Excel and beginning the analysis of Newton. And then the next assessment support, we need to talk about how to write the lab report, like what sections you might have and so on. It should be similar to what you did in chemistry though. Yeah?
Are we going to do math instead of physics Friday and Thursday?
Yes.
So you mean what are we going to do on the regulatory things next week?
I will do the assessment support next week because I want to give you time to get the calculations done for this and the scatter plot. Is that what you're asking me?
So before the class we have to plot every data and not just the Newton, the volt.
No, just this.
Just Newton or just forces?
No, just the Newton one. Because the Newton experiment is the only one you have to type up.
Why did you need it?
Well, that's the experiment.
There's an example. I'm not going to do a Newton example for you, because that would be helping you too much. I have to draw the line somewhere. Because if I do a Newton example, then you'll just change the data in your spreadsheet for the data you got.
Also, we don't actually need it.
Well, of course you need this, because this is the process for calculating the uncertainty and the slope.
I know, but we don't have a report for this, right?
No, I was just using this as an example. Yeah?
For the lab book, you
Yeah.
have to draw the graph and analyze them to find.
Yeah, but for the handwritten lab book, all you can simply do is you just do a quick sketch and then just estimate by measuring this length divided by this length.
Let me just do that, so
If you think that'll be quicker.
just plot and graph it and make a line, that's it.
But you have to put it in your lab notebook. So do you want to print it and then cut it and stick it? You really want to do this? That is fine. I've never had, in 10 years, I've never had a student ask me, can they do this? But yes, you can do this.
Why so fast, like?
You can do this, that's fine. There's no problem. No problem. Okay. Any more questions before I close this?
Can I do?
I have. What do you do with that 2 data again?
With the what?
The split one.
What do you mean?
I mean, we have 2 data, right?
Well, not quite. You have 2 runs which should be very similar, but technically not the same, because the U's and V's are slightly different, since the trolley has a slightly different starting point. But just treat them as 2 separate observations. Don't average them. In other words, you're asking, what do I do? I'm saying, do nothing. Just put all the points down as actual observed points. Don't combine them. It's not like the pendulum. In the pendulum experiment, you had to do everything twice and average. I'm saying, don't do that here.
I know, but if we don't average it, we pick one.
No, use both. Oh my goodness.
20.
I'm speaking English, I'm very...
Also,
Yes!
with like the same weight for 2.
Yes! Yes! Yes!
Can I take a paint?
Yes. What do you want to know?
Something like that.
Oh, this is just an example.
No.
Got this? I hope it's recording. Yeah, it is. Okay. Can I close this now? Yeah?